And thank you very much for the invitation to give a talk here. I want to thank the organizers, Angela, Monica, and Miles. So I'm very happy to be giving this talk on Zoom. First time I give a seminar talk of this nature on Zoom. So what I'm talking about today is about conditional regularity estimates for the Boltzmann equation. Most of this work is joint work with Cyril Imbert. There are also some part of this work that is joint with Clément Mouchot. And this is about the Boltzmann equation. It concerns regularity estimates. Some of the ideas that that apply here originated in the area of non-local equations that you must all know that it's, the analysis of non-local elliptic equation has been a very active area in the last 20 years. And I hope that in this talk I can explain to what extent those ideas play a role here. And so let me start. So what's the Boltzmann equation? The Boltzmann equation is a model from statistical mechanics that stands at an intermediate scale between what would be the macroscopic model of the fluid equations, like the Euler or Navier-Stokes equation, and the microscopic scale that would be this highly dimensional dynamical system that tracks the particle, that tracks the position and the velocity of every single particle in a gas, let's say. So it's a model that for the evolution of the state of a dilute gas, we have this function f that is a function of time t, position x, and velocity v. And what it does is it tracks the density of particles with respect to, so for all times, with respect to their position and velocity, right? So it's like a density description of what would be this big collection of particles. So like I said, it's an intermediate scale between the position of every particle and the macroscopic equation, like the Euler and Navier-Stokes equation. So this one gives you the density of particles with respect to their position and velocity as it evolves in time. And so the evolution of this density is determined by the Boltzmann equation. So how does the Boltzmann equation look like? So imagine for a second that the particles do not interact at all with each other, that they just move in straight lines according to their velocities. So if that was the case, what we would have would be a transport equation, would be exactly this left-hand side of the equation that would be equal to 0 if the particles did not interact with each other. So you see that left-hand side of the equation is a transport equation where each particle moves in space, this is the gradient with respect to x, according to its own velocity. So v is the variable v in the function f. But the particles do interact with each other. So instead of having transport equal to 0, we have transport equal to this collision operator Q, the Boltzmann collision operator that has some complicated form that is written down here. So it takes a while to get used to the form of the Boltzmann collision operator. So I don't want to try to tell you everything. I'm not going to try to tell you everything about it in the first slide. I'm just going to tell you what you need to know as the talk progresses. So what you should see is that it's a quadratic operator on F, so it's a nonlinear operator, and it has some sort of integral structure. There is this kernel B over here, and depending on what type of microscopic model we use for the interaction between particles, this kernel B can take several different forms. So one of the possibilities is what is in the kinetic literature known as the non-cutoff kernels, which have this form written down there. So these are the kernels that come from that would come from a microscopic model in which we assume that the particles would repel each other by some sort of power law potential when they get sufficiently close together. So that kind of microscopic model leads to this type of kernels. Other microscopic models would lead to different kernels B. All right, so there are different choices here. So for our talk, we have to deal with, for the purpose of this talk, we're going to study these non-cutoff kernels, because for these non-cutoff kernels, there is a singularity here that the kernel is not integrable with respect to the variables of integration here. And the collision operator makes sense only because there is an extra cancellation on that factor. And that singularity will have a regularization effect, as we will see. So let me tell you a little bit about the collision operator, but just a little bit. You see that here there's just an F, F star, F prime, and F prime star that are a bit mysterious. So these are values of F evaluated at different velocities, but at the same point in respect to T and X. So when we evaluate Q at TXV, we integrate and we evaluate F at different velocities, but at the same point in T and X. So Q is an integral differential nonlinear operator acting on the velocity variable for fixed time T and position X. So for fixed T and X, you apply this operator Q to the function with respect to the velocity variable. So it's an operator that acts on velocity only. So think about this Q as some sort of fractional order differential operator that acts in velocity that is nonlinear. All right. So we'll do some sort of reductions for Q later on. So something that I want to mention is that the hydrodynamic limit. The Boltzmann equation can be used to recover hydrodynamic equations under some asymptotic regimes. So from the density function, one can define the macroscopically observable hydrodynamic quantities. For example, if I integrate this density function with respect to velocity, we will get the mass density at every time and position, right? If we take the first moment of this density function, so that's integrating F times V, we will get the momentum that when we divide it by the density, that gives us the macroscopic velocity at the point T and X. And if we look at the variance of this density F, we get the temperature. So these macroscopic quantities converge to the solution of the compressible Euler equation in certain asymptotic regime where we enhance the collisions in the Boltzmann equation. So it's this is something I like to use to speculate about what to expect for the Boltzmann equation, because the well-posedness of the Boltzmann equation, the global well-posedness for arbitrary initial data, is a major open problem. So we don't know that if given any arbitrary initial data, the Boltzmann equation will have a global solution that stays smooth for all time. And that's a major open problem that seems very difficult to solve currently. And then I said that I was going to give a talk about the regularity of the solution. So I want to give some regularities that will end up being conditional regularity. So is it reasonable to expect that the Boltzmann equation will stay regular for all time? Or is it more reasonable to expect that perhaps it develops singularities at all time, at finite time? Well, this scaling limit, which is the compressible Euler equation, is known to develop singularities in finite time. To first order expansion, that means if we add some error terms depending on epsilon, the next order expansion would be compressible Navier-Stokes equation with certain viscosity that depends on epsilon. The compressible Navier-Stokes equation is also known to develop singularities, although that's a much more recent result. And so if the scaling limits develop singularities in finite time, should we expect the Boltzmann equation to stay smooth or to develop singularities? Well, it's not such an obvious question. I mean, I cannot really give any proof one way or another, but I would say that it depends a little bit on the type of singularities that these hydrodynamic limits develop. More precisely, there is the simplest type of singularity to show that you can obtain, that you can observe in the compressible Euler equation, is the shock type singularity. That is like in Berger's equation. something comes in this direction, shocks and crashes against something that comes in the opposite direction, and a discontinuity emerges from the flow of the compressible Euler equation. So that's a type of singularity in which all the quantities involved stay bounded up to the time of the shock. So that's not the type of singularity that I would expect to reproduce in a kinetic equation, because the kinetic equation allows different velocities to coexist at the same point in space. So a shock doesn't really produce any problem in the flow of a kinetic equation. In the same way that for the compressible Navier-Stokes equation, I'm not going to have a shock singularity because the diffusion is going to smooth out everything, and the solution will be smooth whenever the functions are all bounded. So shock singularities do not seem to lead to any singularity in the flow of a kinetic equation. However, there is another type of singularity that is much harder to come up with for hydrodynamic equations. That is when some of the quantities, the mass density, the velocity, or the temperature, blow up at some point. So it goes to infinity at some point. And that's the type of singularity exactly that Frank discussed in this same seminar 1 week ago. There are these new papers by Merl, Roniansky, and Silvestre that they prove that there is implosion singularities for compressible Euler equation and for compressible Navier-Stokes equation. And that is the type of singularity that I cannot rule out it would happen for the Boltzmann equation. That means that the fact that the hydrodynamic limits, which is a compressible Euler equation, has this blow-up profile in which everything concentrates at that point. Well, it doesn't quite concentrate, but everything, the density and the velocity go to infinity at some point. I'm not sure if one could. I would believe that most likely than not, one should be able to construct such type of singularity for the Boltzmann equation as well. So, like I said before, the well-posedness for arbitrary initial data of global smooth solution is a major open problem for the Boltzmann equation. But if I had to bet, I would say that with 75% probability, it's not true. The singularities most probably emerge from the flow. So what is it that I'm actually going to talk about? What is it that I can prove? So my realistic program of regularity for Boltzmann equation is a conditional regularity. That is, I'm going to assume the completely unprovable condition that the hydrodynamic quantities, which are the macroscopic quantities that I discussed in the previous slide, stay bounded and away from vacuum. So that is an assumption. It's so I'm starting from a solution that I'm told that these quantities stay bounded. Then I want to show that under those conditions, the Boltzmann equation is C infinity. So I want to get estimates for all the derivatives of every order and the corresponding decay for large velocities in terms of the bounds of the hydrodynamic quantities, and only with respect to the bounds of the hydrodynamic quantities. So like I said, the unconditional well-posedness of Boltzmann equation seems to be completely out of reach. So this is the only realistic scenario in which I can think of that I can prove a regularity result. I'm also assuming that the solutions are away from vacuum. That means that the mass density is away from zero. I'm also going to assume that the temperature density is away from zero. So because the temperature zero and mass zero are also some sort of singularities for the compressible Euler and compressible Navier-Stokes equation. And in particular, I think that for the compressible Navier-Stokes equation, if initially the density is zero somewhere, one can prove that singularities would emerge from the flow. So I'm assuming that they're bounded from above, and the mass density and temperature density are bounded from below. So with this program, so even if we make all those assumptions, the question that remains is if by making all those assumptions, I'm effectively ruling out all these hydrodynamics type of singularities that one observes in the compressible Euler and compressible Navier-Stokes equation. So I'm saying that type of behavior is ruled out by my assumption. But still, after that assumption, one has a question about whether there is any other kind of singularity that would be specific to the kinetic formulation of the equation. So is there any other nature of singularity that one should observe from kinetic equation? And the answer that I'm going to give to that question is no. So this is the theorem. It's a theorem from last year, John with Cyril Imbert. So gamma and 2s are the two parameters in the collision kernel for the non-cutoff collision kernels for the Boltzmann equation. The assumption is that the mass density, that is the integral of f with respect to v, is bounded from below and above by two fixed constants. That the energy density, that's the second moment of f, which depends on t and x, is bounded from above, and that the entropy density is bounded from above. So if gamma is negative, that's this parameter, that is what is called in the kinetic community as soft potentials. We also have to assume that the initial data has a decay at infinity. That's because decay for large velocities is self-generated when gamma is positive, but is only propagated from the initial data for gamma negative. And under these assumptions, so the last one is just an assumption of the initial data, so it's not really important. The three important ones are 1, 2, and 3. There are the assumptions on the solution even after the initial data. So under those assumptions, we get estimates for all the derivatives of all order in terms of the constants in the assumptions only, right? And also the decay as the velocity goes to infinity. All right, so let me discuss some other regularity results for the Boltzmann equation. So there are some early regularity results in the space homogeneous case, that is when the function f doesn't depend on x. In that case, the problem is fairly well understood. And for any initial data, we have global smooth solutions, at least in this range of parameters. Then there is also global well-posedness when the initial data is sufficiently close to equilibrium. And then there is a result that says that if the solution, this is also a conditional result, if the solution is in H5, and it's also away from vacuum, then the solution is C infinity. So this is also a C infinity estimates like ours, but under stronger conditions, because this is requiring 5 derivatives of the solution in space and velocity to stay bounded for all times, and also with some weights that grow a bit algebraically fast as the velocity goes to infinity. So this is a stronger, much stronger condition than the one we described. The one we described is also, in a way, physically meaningful. So let me discuss some consequences of our result before I get into explaining a little bit of the ideas of the proof. So one consequence of the result is a continuation criteria. For initial data that is sufficiently nice, one can prove existence of solutions of the Boltzmann equation in short time. And the time that the solution lasts depends on how nice the initial data is. So with our result, we show that if the hydrodynamic quantities are bounded, then we get estimates of all order of the solution. So effectively, we prove that this short time, that this solution that one gets from the short time existence result can never blow up unless one of the hydrodynamic quantities blows up. So in a way, saying that if the kinetic equation has a singularity, it has to be visible macroscopically, right? So it has to be reflected in one of these macroscopic quantities, right? So you may think about this as comparing it with the regularity result for the conditional regularity for Navier-Stokes. You know, this is Brody-Serring condition that says that solution of Navier-Stokes that is in certain space is C infinity. However, the reason why it holds is very different. In Navier-Stokes, it has to do with scaling. Like all the assumptions move the equation from the subcritical regime from the supercritical regime into the critical or subcritical regime. In this case, the reason why the assumptions, the condition gives us regularity is different. It is because these are the hydrodynamic quantities are the ones that make the collision operator elliptic. But anyway, I'm going to discuss that later on. Another consequence of our result is that it improves a little bit a famous result by Villani and de Villet on the convergence to equilibrium. So the Villani and de Villet have a very well-known result that they prove that the solution to the Boltzmann equation converges to equilibrium, that is to a Maxwellian solution as time goes to infinity, conditional to the solution being C infinity with uniform bounds in time. So they require, they require a lot of derivatives of the solutions to be bounded uniformly in time in order to get this convergence to equilibrium result. So any result that says that if something happens, then the solution is C infinity with uniform bounds would transfer the condition to the earlier condition. So in this case, now the condition for convergence to equilibrium is only the bounds on the hydrodynamic quantities, because the bounds on the hydrodynamic quantities imply the C infinity bounds that they require for their convergence to equilibrium result. All right, so now I'm going to move on and tell you a little bit of an overview of the ideas involved in the proof. So these are the ingredients of the proof. And each one of these has its own story in a way. So today I'm trying to give you an overview of all the ideas involved in the proof. This was a program that took a few years, and each one of these bullet points is its own paper. So I'm going to tell you what they are. So the first one of these ingredients is an L infinity estimate for solution of the Boltzmann equation, depending only on the hydrodynamic quantities. So this restriction on the parameters it applies for this first L infinity estimates, and it's really the only step in which it applies. I mean, it applies in the pointwise decay estimates as well, but for the same reason. So the second step is a weak Harnack inequality in the style of Di Giorgi. So we apply the Giorgi type techniques to get a local Helder continuity estimate. So this gives us C alpha estimate for the solution of the Boltzmann equation. So the first step is the C infinity estimates in terms of the hydrodynamic quantities. The second one is Helder continuity estimates in terms of hydrodynamic quantities. So this case is local, meaning that my C alpha estimates apply provided that we restrict our analysis to velocities that are to small velocities. Velocities smaller than certain number R. R could be anything, but it has to be a finite number in this second step. Then there is Schauder estimates, that improve the regularity, the Helder continuity exponent to a larger exponent. So here we gain 2s derivatives. 2s is this parameter in the Boltzmann operator that is in a way the order of the order of the operator. I said that the operator is an interdifferential operator and it has a fractional order. The fractional order is going to be 2s. And so with the Schauder estimates, we gain 2s derivatives with respect to the Helder estimates that we obtain from the weak Harnack inequality. Then there is also pointwise decay estimates that tells us that this function f is going to decay for large velocities with an arbitrarily fast algebraic rate. These decay estimates are self-generated when gamma is positive, and they propagate from the initial data when gamma is negative. Recall that gamma is another parameter in the Boltzmann kernel. In the kinetic literature, this would be known as, for hard potentials, we have a self-generation of this decay, and for soft potentials, they are propagated from the initial data. And then we need to figure out what happens for large velocities, because for the weak Harnack inequality and the Schauder estimates, we get regularity estimates for small velocities. But then there is a little trick that is a change of variables that allows us to transform any estimate that we make for small velocities into an estimate for large velocities. So the last step is this change of variables trick, that somehow trivializes the analysis of large velocities for the Boltzmann equation. And once we have that, we have this. We have to differentiate the equation and apply the Schauder estimates to derivatives of the equation to get higher regularity estimates and iterate. So this is the outline of the whole program for regularity estimate, conditional regularity estimate for the Boltzmann equation. So what I'm going to do now is I'm going to give you a short description of each one of these bullet points, what it is. So I'm going to go back to each bullet points one by one, and I'm going to try to explain what it is and what the result is specifically for each one of these ingredients in the proof. All right. But before discussing that, I have to explain to you. I have to go back to the collision operator and discuss a little bit more what the collision operator is and why it is an interdif. Why can I think about it in the context of non-local equation and interdifferential equations the way it was developed in the last 15, 20 years. So this is the original form of the Boltzmann collision operator, the way it was written in the first slide. If we do a change of variables and some manipulation, we can write it in this way. So the first term is an interdifferential diffusion. So it's a diffusion operator with a kernel that depends on the solution f itself. So think about it as a quasi-linear equation. You know, if you have a second order parabolic equation, in a quasi-linear equation, it could be an equation whose coefficients in front of the diffusion depend on the solution itself. So this is kind of like that, except that it's not an ordinary second order equation, but an interdifferential operator, but a non-local operator. So here the kernel depends on the function in a way that has to be specified by some formula that can be computed from the original representation that I have on top. And then there is a lower order term, which is f times the convolution of f with any given function that is typically just v to the power gamma. So the change of variables that we perform here happens to have a name, which is called Karleman coordinates. And when then there is a computation to get this kernel f, get this kernel k sub f. So after this computation, I want to say this again. Think about the Boltzmann equation as a quasi-linear equation. So it has a first term, which is a diffusion term, which is interdifferential diffusion, depending on some kernel that depends on the function. So a priori, we know very little about that kernel, because for every solution of the Boltzmann equation, it's going to be a different kernel. And then there is a lower order term. So let me tell you roughly how the kernel looks like. So this kernel k, for any point v prime, is going to be the kernel of the fractional Laplacian. This is v minus v prime to minus dimension minus 2s. This is exactly the kernel of the fractional Laplacian, the Laplacian to the power s. The Laplacian to the power s is a non-local operator with exactly this kernel. But it has this factor over here, which is the function f multiplied times some weight and integrated along the plane that is perpendicular to the direction from v to v prime. So if we have v here and v prime here, the kernel k sub f is the kernel of the fractional Laplacian multiplied times some weighted integral of f along this hyperplane. Now, in the very first step of the analysis, at the very beginning, all we know about f is given by the hydrodynamic assumptions, by the bounds on the mass density, energy density, and entropy density. So there is nothing we know about f on the way it integrates on hyperplanes. In the, I guess I should say, classical literature in non-local operators, the most typical assumption on kernels is that they're bounded below and above by a multiple of the fractional Laplacian, which is what we would get is this factorals bounded above and below. But there is no way we can get a bound below and above of this kernel in terms of the hydrodynamic quantities only. If all I know that f is a bound from below and above of the integral of f, I cannot conclude anything about the integral of f on hyperplanes. So our kernel k sub f is not uniformly elliptic in the most canonical way. It will be uniformly elliptic in a much more relaxed way that we have to figure out. Okay, so it's only going to satisfy a much milder form of non-degeneracy, which is what I'm going to explain in the next slide. So the kernel for the Boltzmann equation for any solution f satisfies the following symmetry, which is the symmetry that corresponds to non-divergence types equation. Why is that? You know, in non-local equations, there has been a lot of work about reproducing regularity estimates from second-order theory. And when you work with, when we try to reproduce the methods of elliptic equations in non-divergent form, you typically make this assumption on the symmetry of the kernel. There is a different type of symmetry assumption that you will have to make to reproduce the methods of elliptic equations in divergent form. And that's not the one we get, which is in a way inconvenient because I want to apply the Churchy-Nash-Moser theory, which is a theory for equations in divergence form, which is the symmetry condition that we would need to apply methods in the flavor of Kirillov-Safonov theory. But that's not what I'm going to do because I cannot do it in kinetic equations. So the non-degeneracy from below is that the kernel K is bounded from below by a multiple of a fractional Laplacian, but only in certain cone of directions that changes from point to point. So at every point, we have a cone of directions along which the kernel is bounded below. So that's the only non-degeneracy we have for the kernel. We don't have this bound to hold at every point, but only for those V prime in a cone of directions starting from V. And the upper bound is only on average. So if we take the integral of K in with respect to V prime in a ball center at V, it's going to integrate to something that has an upper bound, which is the same upper bound that we would get if we replace the kernel K with the kernel of the fractional Laplacian. So instead of having a pointwise bound from above for these kernels, we have a bound from above on average only. All right, so it's a much milder form of uniform ellipticity, if you want. So now we have to try to, the question is, what kind of regularity results can we get for integral differential equation with this type of kernels? So it's a question that now we have to go back to the theory of integral differential equations and sort of work to improve the results in integral differential equations to accommodate for these more degenerate kernels. So the first thing that I want to show you is a corrosivity estimate. So it turns out that the cone of non-degeneracy, if you have a kernel, I mean here the T and X is irrelevant because I'm evaluating for every T and X fixed. But if you have a kernel that is bounded from below in a cone of directions, so for every V, I'm saying there is a cone of directions along which the kernel is bounded from below by the kernel of the fractional Laplacian, but only on that cone of direction, then that's enough to get a corrosivity estimate. That is that the quadratic form associated with this kernel is bounded from below by the HS norm of the function locally, right? And this is a property, there's a generic property for integral differential operators. You give me any kernel that satisfies this bound from below on cones, and then the corrosivity estimate holds. So it's a generic property of integral differential operators that in particular applies to the kernel of the Boltzmann equation as well. Interestingly, in the Boltzmann literature, this corrosivity estimate it has been known for a while already, and with proofs that are specific to the Boltzmann collision operator. So people will always put here the Boltzmann collision operator multiplied times F and get this corrosivity estimate. But it's also something that one can imply directly from this general condition of integral differential operators. Okay, and let me say that it is a sufficient condition to have corrosivity on the integral differential operator, but it's not a necessary condition. And necessary and sufficient conditions to to get corrosivity of interdifferential operators is not a well understood subject. Okay. So I said that the first thing I wanted to apply to get the local Hurdle continuity was some version of the Cauchy-Nash-Moser theorem, but for kinetic interdifferential equations. So let me remind you quickly what the Cauchy-Nash-Moser theorem is, the classical one. So the original de Cauchy theorem was for elliptic equations that says that if you have a solution of an elliptic equation like this, that the coefficients are uniformly elliptic, then the solution is Hölder continuous. And it provides an explicit bound for its Hölder law. And it's important that the estimate depends on the uniform ellipticity of the coefficient, that is on a bound from below and a bound from above for the coefficients, but it doesn't depend on any regularity for the coefficients. Because I want to apply it to a nonlinear equation that a priori the coefficient depends on the solution, so if I want to prove the regularity of the solution, I cannot assume any regularity of the coefficients. There is a kinetic version of the Cauchy-Nash-Moser theorem, which is fairly recent. I mean, you can see here how it developed. So originally, like I said, it was for an elliptic equation with the coefficients here. So there is an extension for a Hölder estimate for a kinetic equation whose diffusion is an elliptic operator with variable coefficients in V only. You see that the diffusion is only in the variable V. So the transport part is transferring somehow the regularity from the V variable into the space variable. And for equations on this form, one can still apply the Cauchy's method, of course with some new ideas as well, to get Hölder continuity of the solution. So there was this first work by Pascucci and Polidoro, proving only the first part of the Cauchy estimate, that is the L infinity estimate, in terms of the L2 norm of the function. Then there is a paper of Wang and Zhang getting the Hölder continuity. And then there is a more recent paper by Boltzmann, Mouchot, and Vassor. And they do a proof, a new proof using the Cauchy technique, and they also reduce the Harnack inequality for this type of equations. So what we did is an interior differential version of that result. That is, we have transport equation, but now we have an interior differential diffusion. And so this is the type of result that we would need to get local Hölder continuity for the Boltzmann equation. Because in the Boltzmann equation, we end up with that the function f satisfies an equation like this when k and g depend on f somehow. But as soon as we prove that k on f satisfies the assumption of this theorem, then we can apply this theorem and get the Hölder continuity estimates. So the proof of this theorem is somewhat complicated. Let me say that there are three main difficulties that one has to deal with. First, that the diffusion takes care in V variable only. So of course, one has to figure out how to get regularity in the X variable as well, using some sort of hypoellipticity of the equation. The other difficulty is that the kernels K are not just uniformly elliptic in the most convenient way, but they're uniformly elliptic in the most degenerate way that I described before. And they are not symmetric in the way that we would want them to be symmetric. They are symmetric in this non-divergence types way. So there is certain cancellation that I didn't specify before that the kernels of the Boltzmann equation satisfy, and that cancellation is enough to apply non-divergence form techniques and deduce this the Cauchy type result. So that's three things that will appear in the proof of this theorem. Okay, so from this theorem, one gets local Hölder continuity results, local Hölder estimate for the solution of the Boltzmann equation. Now, I want to stress that these Hölder estimates are not uniform for all velocities, because the non-degeneracy results for the that cone of directions and those upper bounds for the kernel degenerate as the velocity goes to infinity. So we can only get the non-degeneracy condition for the kernel for bounded velocities, and therefore we can only get these Hölder continuity results locally for bounded velocities. All right. So after we have discussed the Cauchy type result to get local Hölder continuity, we want to get Schauder estimates to improve the order of differentiability. The Schauder estimates is this classical result for elliptic equations. Like you have an elliptic equation in non-divergence form, whose coefficient on the right-hand side are both Hölder continuous, then the function, the solution U is C2 plus alpha. So you gain 2 derivatives from solving the equation. You gain 2 derivatives because the equation is of order 2. If the equation is of order 2s, like in the Boltzmann equation, we're going to gain 2s derivatives. There is a longer history of variants of the Schauder estimates for kinetic equations. But in this case, they are really actually particular cases of the more general theory of hypoelliptic equations. So in the hypoelliptic settings, there is a long history of results of Schauder estimates. And also for interdifferential equations, there are some results about Schauder estimates, both in the elliptic and the parabolic case. What we did was an interdifferential version of the kinetic result of the. We wanted a Schauder estimates for kinetic equations with integral differential diffusion. So here is our result also with Silvestre. If we have this is the symmetry, exactly the symmetry for the Boltzmann equation. So this is because we are in the for the Schauder estimates, we need non-divergence type symmetry. So it's in this case, it's a more favorable scenario. So we only assume the mild non-degeneracy conditions for the kernel, that is in this mild notion of uniform ellipticity, and some sort of Hölder continuity. Then we get that the solution is C2s plus alpha. So it's a Hölder continuity result, but with a very specific exponent. You know that the Chorchi method gave us some initial Hölder continuity. So the initial Hölder continuity for the function, since the kernel depends on the function, gives us kernel continuity for the kernel as well. So then we can apply this Schauder type estimates to gain even more regularity for the solution. But this is still local in the sense that we cannot do it at this point yet. It cannot be done uniformly for all velocities. And with respect to the proof of this theorem, let me say that we follow the proof. We follow the ideas of the proof of Joachim Serra for interdifferential equations and adapt it to the kinetic setting. Yeah, I don't have so much time, so I'm not going to say much more about that. Then the next ingredient in the proof or in the program is to get a decay for the function f as the velocity goes to infinity. So this is something that we did also with Clement-Mouchot. So if gamma is this parameter in the Boltzmann collision kernel is positive, that is known as hard potentials in the kinetic literature, we get that f will decay pointwise as v goes to infinity, and this upper bound is self-generated. That is irrelevant. The initial data is independent of the initial data. It only depends on the condition on the hydrodynamic quantity, which is of course a strong condition, right? But at least it doesn't require the initial data to decay. So if the hydrodynamic quantities are bounded, then the function will decay as the velocity goes to infinity faster than any algebraic rate. When gamma is negative, that is for soft potentials, we have to have an initial data that already has a decay, and then we see that those bounds are propagated for positive time. Now, unlike the previous two estimates, unlike the Chorchi type result and the Schauder estimate, this result is specific for the Boltzmann equation. The previous two were true for any kinetic equation with any interdifferential diffusion. Now, the fact that the Boltzmann equation happens to be expressible as an interdifferential diffusion is what allows us to apply in particular the Chorchi result and the Schauder estimate for the Boltzmann equation. In this case, this upper bound is only for the Boltzmann equation. So we apply the specific structure of this quadratic collision operator to get these upper bounds. All right, so once we have all these bounds, the next step is to make them uniform. Well, here we have exactly what this is exactly how the upper bound is behaving for large velocities. We need the regularity estimates to be global for all velocities. We have the Chorchi technique and Schauder estimates that apply only locally, and I want them to apply globally for all velocities. So the problem for that is that the non-degeneracy conditions, in particular, the cone of non-degeneracy, where we have the lower bounds for the kernels, degenerate and deteriorate as the velocity v goes to infinity, right? So I didn't explain exactly how the cone of degeneracy is computed. So I don't know if you remember that the constant in front of the constant in front in the diffusion kernel was an integral of f on some plane that was perpendicular to the direction between v and v prime. So here is v, and v prime is somewhere in this green cone in the perpendicular direction. The idea is that we will hit the set where f is large. F will be large somewhere, typically near the origin, right? So if you have a point v that is somewhere far away, there will be a cone of non-degeneracy that is the dual cone of the directions from v that will hit the set where v is large. So we have this cone of non-degeneracy where fk is bounded from below. This cone of non-degeneracy will become narrower and narrower as v goes to infinity. So we don't have uniform ellipticity bounds, uniform for all velocities, so that we cannot apply the Cauchy and Schauder estimates uniformly for all velocities. So what we do is we're going to do a change of variables that opens up this cone of directions and makes it of a fixed width, right? So we take a change of variables, which is fairly simple and explicit to compute, that is going to open up the kernel and fix the width of the kernel. So we take this map T0, depending on the velocity V0 on this velocity here, and we make a change of variable that opens up the cone of directions. Now, we also have to change variables in T and X to preserve the transport part of the equation, but the integral part of the equation will change because of the change of variables, and we'll have a kernel that is bounded from below in a cone of direction of fixed width. So at least the lower bound will be uniform after this cone of direction. And then we computed the upper bound and the cancellation conditions, and here is where we got lucky, because it happens that all the other bounds, the upper bound on the kernel, the cancellation condition, and all the other bounds involved in the estimates that we computed actually are uniform after the change of variables. That is, none of them depends on the point V where we start the change of variables. So because of that, all the regularity estimates, like the Schauder estimates and the Cauchy estimate, will be uniform after the change of variables. So I'm summarizing that in this slide. So after we do the change of variables, that is made with the purpose of making the thickness of the cone of the non-degeneracy fixed, then the lower bound on the kernel on this cone of degeneracy will be uniform with respect to the center, the point V where we center the change of variables. The integral upper bound on the kernel is also uniform, and the cancellation conditions needed for the weak-Harnack inequality are uniform. Therefore, the weak-Harnack inequality can be applied with uniform parameters after the change of variables. But the change of variables is explicit, so we can explicitly compute how the Helder estimates behave for large velocities. We can explicitly compute what the Schauder estimates, how the Schauder estimates are going, what the Schauder estimates gives us for large velocities. And something is interesting to point out for those familiar with in the kinetic community is that the usual distance between points V and V prime becomes the anisotropic distance of Boltzmann and strain after the change of variables. So, that's some link with the earlier theory. And in fact, the coercivity estimate, the basic local coercivity estimate, becomes a coercivity estimate that was in the work of Boltzmann and strain after the change of variables. So we put it all together. Now, if we, I guess logically, the starting point would be the fast decay for the solution. That is, we have an upper bound that decays for large velocities. Then from the weak-Harnack inequality, combined with the change of variables, we get global Helder estimates. With the Schauder estimates, combined with the change of variables, we get a global Helder estimate with a higher exponent. But then we differentiate the equation, and we apply the Schauder estimates to derivatives of the equation, or to incremental quotient of the equation. Remember that the Schauder estimates were sort of a generic estimate for any kinetic equation with an integral differential diffusion. So we can apply it to derivatives of the solution of Boltzmann and get higher and higher regularity, and that's how we get say infinity estimates. Okay, so that's basically the outline of the whole proof of our regularity results. So maybe I'll finish the talk by mentioning a few open problems. Some open problem that one can consider is a weaker continuation criteria that would be, I don't know if the bounds that I gave on the hydrodynamic quantities are the least one needs to assume in order to get a continuation criteria. There are some results by Henderson, Snelson, and Tarfulea on the Landau equation that by analogy makes you believe that perhaps for continuation criteria, that is to ensure that no blow-ups takes place if you start from a smooth solution, perhaps only an upper bound on the mass and energy is all you need. Regularity results for gamma plus 2s outside of this range would require further ideas, and I think it's complicated. For cutoff case, there is no way one can get any regularization result, but perhaps the continuation criteria would hold. I think actually that's very likely to hold, but we have never worked on cutoff case. Bounded domains, we worked on functions that are periodic in X. One can also work in a bounded domain in space and put some physical boundary condition. That's some further analysis that will be needed, especially to understand the regularity close to the boundary. And unconditional regularity, that is, we remove completely all the hydrodynamic assumptions and try to prove regularity for the solution of the Boltzmann equation for all time, for all initial data, because we're very ambitious. I would recommend that if you think that's a problem that you should solve, you think first about the millennium problem for the Navier-Stokes equation, because that's probably easier. So a couple of weeks ago, we posted an article, a survey article with Cyril Imbert on the archive that has more open problems. So I guess I have to stop here because Monica is looking at me. So I'm done.